Our last speaker is Tara Javidi. Tara, are you here?
Yes, I am.
Yes. Hi. So Tara
Hi.
is a professor at UC San Diego and the founding co-director of Center of Machine Integrated Computing and Security. So she's an expert of so many things, ranging from active learning, information theory with feedback, stochastic control, and to statistical inference, and so on and so forth. I cannot list all of them. All these topics are really related to and relevant to this integrated sensing and communication. So that's why we want to hear from you. And today she will deliver a talk on active and dynamic beam tracking and alignment for mmWave. So please.
Thank you so much, Mari, and Giuseppe and other organizers. This is really, it's really sad because I really wish this was in person so I could spend more time in the discussions and all that. So I'll just try to be fast. This is work that my former PhD student, Dr. Seung-Gun Chiu and Nancy Ronhalio did. They're at Samsung and ISAC currently. Oops, no, I don't know why this is. Okay. So, so I'm going to go fast. I assume that you are all much better experts. I just like to set the ground because I come from this problem from a rather information theoretic and a caricature of the problem. So I just want to sort of set the grounds for what I'm going to talk about today. So I'm considering a very simplistic setup of 1A to D, basically a phased array of a sort. I'm interested in sort of the classic setting of, a simple additive noise model on top of that. So the notations don't really matter. What I would like to emphasize is this impact of the sort of beamforming weight controlling the signal strength in this simple model, if you wish. So I basically have this beamforming gain that I can play with, and what I'm really interested in, ideally, I would like my beamforming weights to do two things. If they cover the angle of arrival, I can capture the signal, so my signal strength will go up, and for communication perspective, I would like this beamforming to be so narrow to actually sort of focus the energy. So from a very high level, this is sort of the connection to the joint sensing and comm. So if I could sense where this transmitter is, I could sort of make sure that my beamforming vector WT covers it. And then for communication purposes, I would like to focus this energy and receive it. So that's sort of high level. It's a soft communication and sensing independent of what XFP is, whether it's pilot or whether you know it or not. This is sort of this soft question. So this is a long list of publications that we have had on this topic. The reason I put it up is to sort of refute what Robert was saying in terms of theory is easy and fast. The first paper that we posed, sort of an information theoretic version of this, was to connect the joint source channel coding with feedback with this tracking problem, where you can sort of think about the source coding part as the sensing and the channel coding part as the part that allows you to communicate. And it took us almost 10 years to turn that caricature problem to the problem that I'm going to talk about, which is the last bolded paper, where we really try to turn that into something reasonably convincing to practitioners. So I just want to say theory is not necessarily, it might be easy to write that first paper, but to make an impact, it takes a really long time to educate yourself. So I don't understand why there's a delay. So so let me just get back to the problem and simplify it even further. So as I said, ideally, I would like to control the beamforming weight such that I can, in the angular space, and here I'm going to simplify again, in the angular space to make sure that I have basically a coverage of my angle of arrival, and make sure that it has a small support so I can get the maximum beamforming gain. So now the challenge in the setup where you have mobility is that the angle of arrival is a time-varying stochastic process. So in some sense, you have to constantly, you have to constantly sort of trade off this sensing and communication in a soft way, as well as in a more a hard way, by controlling your pilot versus data. So if I know X of t, it's useless for communication, but it helps me with sensing because now I know what I'm looking for, versus if I don't know X of t and its data. So prior work in this domain, which we were highly motivated by, it's not a comprehensive one, and these are the work that we thought sort of gave a first step that helped us. Are the first two, they sort of work in the world of predicting and following, whether it's with a filtering strategy where I'm showing it in orange, or whether it's just a sort of a way of predicting the velocity, knowing where you're going, and sort of a very simplistic filter where you just sort of track the angle of arrival. And work with the narrowest beam to sort of follow the transmitter. And then when they have some sort of a threshold on either normalized power or mean square estimate error, and if these are not of high quality, they sort of go say, I can't really communicate, and go to a pilot phase where they actually do re-estimate the angle of arrival. There is a kind of an alternative work that you can sort of widen the beam. Instead of working with the narrowest beam, you widen the beam somewhat to accommodate for mobility in that range. And then when you lose track of the transmitter, you do recurring a local sounding to find it. So the takeaways is that you can do a lengthy re-estimation phase to to basically account for highly random mobility, and unpredictable movements are really the sort of the pain point for all of these methods. Here I'm showing you a really simple setup. When you have a complete predictable movement, the two strategies that work based on prediction and follow, or filter and follow, as you can see, they do very well. They spend some significant amount of time in the pilot phase or alignment phase, if you wish. And then because they're working with very narrow beams, they can just sort of follow, and they have a predictable model they follow. In contrast, the sort of a wider beam, of course, now the design parameters, how wide is your wider beam? So the wide beams that are relatively narrow is the top figure, then you actually end up losing this transmitter, because you're ignoring the prediction in the model, and you have to recur a lot of sounding, versus the sort of widening the beam and sort of communicate with wider beams, so you lose the transmitter less and your piloting is less, so the overhead is lower. Of course, what you really would like to really understand is what happens when the mobility is random, right? Here, I've just given a really simple setting where the transmitter is relatively static, but it has this Gaussian noise that gets added up. So as you can imagine, this is an additive Gaussian noise in the system. So very quickly, what do you think is going to happen is not true. So you lose the transmitter after a while. A cumulative error builds up, and in all of these methods, the time that you actually go back to estimation becomes significant compared to the communication time that you have. And you can also say, what do I care about angle of arrival? I really care about the sort of the normalized beamforming gain, the quality of my communication. And this is sort of looking at the same object from the different angle of normalized beamforming for the Gaussian mobility. Another mobility model that you can think is very common, and it's a good model for mobility, is almost constant and then sort of sporadic jumps. And again, the same thing happens that in these models, if you don't have a good handle on this stochastic mobility, what will happen is that you lose the transmitter, and none of these methods can do quite well, with the exception of the lowest one, where you have given up from the get-go on having narrow beams. So the gain is low, but you basically sort of are following, and you're not following, but you're covering a larger angular space. So you don't lose your communication completely. Again, maybe a more realistic way to think about this is looking at the normalizing beamforming gain. And you see that even though these wider beams have a worse beamforming gain, overall, because you stay sort of covering the angle of arrival from the transmitter, you get a better performance surprise. So what is the sort of the main insight looking at this prior work is that wider beam allows you to do better in terms of alignment or sensing. So you actually know, because you cover the transmitter, you know more about where it is, versus sort of the communication. Narrower beam will give you a better beamforming gain. So our proposal has been to try to do this, to take the components of these methods and combine them by saying, I can use I can sort of have a soft widening of the beam as I lose, as I predict that I will lose my connectivity, and sort of sequentially choose these beams as you go, and that will require sort of keeping track of some sort of a posterior on your angle of arrival and allocate pilots and data. By the way, I want to say in all of this, I'm ignoring the effects of the unknown channel. This is the sort of a code design, but here for simplicity, I'm just focusing on the case that the channel gains are all equal in all directions. So let's say line of sight, in communication. So just to show you the result, when you do this sort of posterior evolution and dynamic variations of your beam as you go, you can revert to pilot signal very rarely. And you can sort of take advantage of the stochastic model that you have for your mobility and sort of try to track the angle of arrival much better. And more importantly, again, the normalized beamforming gain that you get on average is much higher. So in the remainder of my time, what I would like to talk about is the design of the algorithm, the components of it. Again, I apologize, these are very simplistic, looking from a theory perspective, trying to match what we know from the binary setup with the codes. And then I'll talk a little bit at the end towards making a more realistic solutions. So the key features of our algorithm is, first of all, in terms of the beamforming codebook, we have gone the simple path of picking up basically the codebooks, beamforming codebooks from prior work, where folks have built almost ideal beams, in the sense that you have almost a good coverage in the area that your beam is covering in the angular space, almost equal coverage, and try to kill the side lobe outside. So these are and they are hierarchically structured, so I can use them in ways that are reminiscent of the channel coding, sequential channel code. Now, on top of that, the second component, as I said, is a posterior belief about the angle of arrival. Here, the sort of the purple addition to this graph, I don't know if this is visible, if my cursor is visible. This is the posterior, and I have overlaid it with these beams. So in other words, you can sort of right off the bat, looking at all the beam code words that you have sort of an estimate of what is the probability that you catch the transmitter if you use this code word. So here you can see that your probability is going to be really low, basically the integral of this posterior in this space, while here the probability is very high, but you won't know where the transmitter is in that space. And you can sort of go down this hierarchical code book and sort of estimate the probability. Now, the second, and the goal here, and this is the information theoretic sort of insight, is we would like this probability that is the coverage of your angle on top of the posterior to be as close to half. You want it to be as unexpected as possible. So this is this hierarchical posterior matching that we had done in the theory domain that we are mimicking here. Now, the next piece is really evolving the posterior. Every time you make a measurement, you basically, it tells you a confirmation, given the SNR that you're measuring, whether you are covering the transmitter or not. Here, for example, Y of t was high power enough that it tells me, you know, my angle of arrival was covering this half of this lobe, and you can see that I have increased my posterior probability that I'm covering the transmitter and the angular space between, you know, 60 degrees and whatnot. Now, this is the first step. This is based on your observation. You filter out your posterior. And then here is where nicely you can account for mobility model. Your mobility model now allows you to sort of do a prediction step of where you think this posterior will go, given what you predict about the mobility. Here is when, if you have you know, a fixed velocity, which is fully predictable, all you will do is shift. And that's where you account for prediction versus, you know, predictable part of mobility versus the unpredictable part, where it just will fatten the you know, this posterior. Now, as I said, so far, this will give you a soft sort of trade-off between sensing and calm. There is also a harder trade-off that is at your control, which is, should I transmit a pilot signal or a data signal? The benefit of a pilot signal is that, you know, basically it allows you to really estimate better. You get a better SNR versus a data symbol that you know, all you can do is do an energy detection on. So basically now this is gonna be a sort of a trade-off between learning the angle of arrival, the mutual information between what you're seeing and the angle of arrival versus the capacity or the spectral efficiency that you gain using a particular. And this is, again, you can see that if WT is wide, it has larger, you know, with probability close to a half, it has a larger mutual information with the angle of arrival versus if you cover large, you know, if you narrow down and communicate with higher range. This is how this algorithm achieves a far better performance for, I'm showing you with different mobility model. The top model is a predictable model. As I said, it will take you a while to narrow your beam and find the transmitter. And then because it's a predictable model, you're just shifting the posteriors and you're just sort of doing what the other algorithms are doing in terms of track and follow. The interesting case is when the noise gets added, you will lose periodically, you will lose the transmitter, you widen a little bit and you sort of narrow in a dynamic fashion. I'm not showing you the width of the beam that we are using, but basically on that code book, hierarchical code book, you decide constantly on which level you're going to work and follow accordingly. The really interesting one is this sort of angular jumps that you have, this sort of your static and suddenly you move, or your you know, dominant path suddenly switches. Those are the ones that if you have a good mobility model, you can sort of predict that this is going to happen. So you actually kind of doing the jumps, and sometimes you match and sometimes you need to go back to pilot and re-estimation. And this is the same thing. There I was showing you the angle of arrival, how well I can estimate the angle of arrival. This is really showing what you would technically be interested in, which is the normalized beamforming. And as you can see, because I don't widen the beam that much, most of the time just the soft widening of the beam will get me will give me a good tracking. I can get fairly high beamforming gain. And this is showing what I had been showing you and just summarizing. While other methods and in under stochastic mobility end up losing the communication a lot, this method allows you to remain sort of aligned and uses this sort of extra degree of freedom more actively. So let me summarize. I'm good on time. I was hoping to do a 20 minutes, and so I leave a lot of time for discussions. So and I hope I'm not too bad on time. So in summary, we have proposed this algorithm for dynamic beam selection, and we have shown that this dynamic arrangement of beamforming allows you to do this soft trade-off between comm and sensing. So while wider beams in a soft manner will do a worse communication, provide a worse communication link, they allow you to sense and sort of remain aligned, versus narrower beams that allow you to communicate a lot. But if you have a little bit mobility, they're very hard to keep the alignment. And then on top of that, trade off the pilot versus data. So ongoing extensions is the first thing that I'm really interested in. This is joint work with my colleague Pia Pal. We're really interested in co-design of the beamforming code words. Right now, because of our background looking at this from an information theoretic, binary, symmetric channel kind of world, going from binary code words to waveforms will require us to really think about the geometry in much more interesting ways. So that's the first step. We have done some work on mismatch or unknown mobility model, and I would argue a lot of people have used reinforcement learning or other ML techniques to sort of do the alignment, and it covers both, like it sort of like captures both this sort of physical reality that the models we have been using are using to improve on the tracking, as well as the mobility models. And I would like to argue that the right way is to separate learning the mobility model, which is a really good problem for data-driven techniques to help us with, because the mobility models can be really improved, while the physics based and sort of information theoretic way of arguing and thinking about beamforming is really the right way to capture the physics of this. And this is some work we're doing and trying to sort of use ML techniques to learn the mobility and then feed that mobility into the model. And in that, I should say that there is a really interesting questions about can we actually estimate the velocity versus estimating the location? And this is something that I'm really interested in understanding better. But at this point, our work is a little bit, the models are too simplistic to even give you that. Extension to multiple A2Ds. Right now, I'm talking about one scalar or one complex number representing everything for every measurement. You have many antennas, so the more A2Ds you have, the more you can extend this geometric arguments. And this is sort of related to this co-design of beamforming code words and the design of the waveforms rather than beamforming. And then extensions, the more traditional extensions is two-sided beamforming. Right now, I just constantly focus on the receiver. There's nothing that prevents us to do two-sided beamforming, transmit side, and so on. It will just need to have some communication side channel to feed back information. And I will sort of stop here and take questions. Okay, I don't see, maybe I should.
Thanks, Tara, for your great talk. We have time for a couple of questions now. Since you are the last speaker, I think we can take a few questions from the audience.
Maria, I think someone posted the question in the chat.
Oh, I'm missing it.
So the question is, can you please give some insights on how important angular resolution in angle of arrival estimation? If so, what is the practical resolution required for wireless communication applications? Can you see the chat, Tara?
Yeah, I'm trying to understand the question. So first of all, I should have emphasized that in the work, we assume you have many antennas, so you can technically get to infinite resolution in terms of angular space. And if I kind of know exactly the angle of arrival, that's sort of the upper limit is the number of antennas you have, which here I am not considering. I guess the practical aspect of it is that will translate to how much beamforming gain you have, and in these phased arrays, that's critical to beat the path loss. But I leave it. I mean, I think there are people who are much more informed about the practical settings here than I am, so I kind of leave it to them. Here, I mean, in our model, we really wanted to emphasize that if you have mobility, the resolution that you might have to sacrifice the resolution in order to keep the alignment. And the ability to sense and do like almost like a sanity check. If you're communicating with wider beams, just doing an energy detection will tell you, did I lose the receiver or not? So even that one bit of information in terms of sensing really helps. You know, practically how much you can do, it really depends on how much mobility you have on that end. Giuseppe.
Hi.
Hi.
I didn't understand one thing. So you're considering basically transmitting with the beam, and then you're optimizing somehow the width of this beam and following the direction, somehow doing some kind of tracking.
Yeah.
But what is the observation to your model? So what is coming back?
So yes, so maybe I should have not rushed it. So I'm assuming the transmitter have a sharp beam that is sending roughly towards the receiver. Think about like a receiver that is stationary on a pole, and a car that is driving by. So the car roughly knows the pole's direction. So it's sort of being you know, has a narrow beam towards the receiver, and then the receiver has a phased array more or less, that it has multiple antennas that sees this and just has one scalar, which is sort of the inner product of your weights with the, you know, the frontier of the beam that it receives, and you just get that one complex number that is the output of your HUD. Does that make sense?
Yeah, that's the receiver, but is this like conveyed back? So there must be some kind of feedback, whether it is generalized feedback.
So we focus on the receiver end to avoid the feedback. So if you think about the side information, is the assumption that the transmitter roughly knows where the receiver is, and it just targets something around the receiver, and the receiver is just changing. And that's all it needs to know. If you were to go with just, let's say, communication, then I am just estimating whether I caught your signal or not? And if I caught your signal, what is your signal? So I'm sort of doing the COM with that assumption.
Okay, so
I don't need to
this
feed
is,
anything back.
This is just an adaptation of the receiver.
At
You're
the receiver.
adapting the receiver.
And but then you are very smart to notice that if I have this dynamic estimation going between the pilot and data, I need to be sync, so I know that the receiver missed me, so the transmitter switches back to pilot, and that's the communication channel that we need. Sort of one bit of feedback that says I lost you. Go to the pilot phase.
Okay. Mm-hmm. Thank you.
Yeah.